Welcome, everybody, to today's CDAC webinar. I'm pleased to introduce today's speaker, Dr. Amy Coleman from Livermore. Amy is an experimental physicist with an interest and expertise in high energy density science, and in particular, the use of laser dynamic compression methods to explore the behavior of materials to megabar and even terapascal pressures. Though early in her career, she's already led a number of exciting studies that also include the development of new diagnostics, such as X-ray diffraction, XFs, and this leading to structural studies of both solids and liquids under extreme conditions. And most recently, she's published a very nice phys-rev letter on record compression studies of gold to terapascal pressures. She's also leading an important internal Livermore LDRD on developing new temperature measurement diagnostics, which I think she'll tell us about. Amy has a master's and PhD in physics from the University of Edinburgh. She was a postdoc in Edinburgh before moving to Livermore and then joining a permanent staff in 2019. Thank you very much, Amy, for agreeing to give this talk in this very busy time. We look forward to it.
Nice. Thank you for that introduction. Yes. So, today I am going to be talking about exploring extreme states using sort of tailored compression paths. Let's see. So, the techniques that I'll primarily be talking about today are laser-driven dynamic compression experiments, right? And so to kind of give an introduction to this talk, I wanted to briefly flash up this lovely image, which was designed by the Lawrence Livermore Lab design team in the wake of our recent gold PRL paper. What's going on here is this is an artist's interpretation of a diffraction experiment at the National Ignition Facility. So we have our sort of TARDIS diffraction diagnostic platform in the middle here. We have a target. I'm sure everybody will be disappointed to know that we're not actually shooting full solid gold bars on NIF, but it looks nice in this picture. We have sort of a version of diffraction of X-rays coming through and giving us diffraction on our image plates. We have a couple of floating crystal structures at the top, a face-centered cubic and a body-centered cubic. There's a lot going on. Hopefully, by the end of this session, everybody will feel more familiar with what this image is representing. Now, in this field of dynamic compression, developments in technology and technique have really allowed us to push the limits of what is achievable in terms of reaching extreme pressures. But the central problem is no longer just reaching these extreme states. We also have the problem of controlling our compression path for a more thorough exploration of thermodynamic states. And today, the topic that I want to discuss specifically is how can we deliberately access the continuum between traditional shock and traditional ramp compression experiments, and also simultaneously, how can we constrain those states adequately thermodynamically? So I'll talk through sort of the intricacies associated with physically and practically realizing these experiments, and then I'll give some examples of published work and some unpublished ongoing work. And then at the end, I'll begin to describe some emerging techniques which are really sort of revolutionizing the game for us in dynamic compression. So to begin with, just to kind of get everybody orientated, I'd like to contextualize what we're talking about when we're talking about extreme conditions. Probably this is not necessary for many people in this audience, but personally I find it nice to sort of remind myself really what we're looking at in these experiments. So if you imagine sort of the conditions that we're all sitting at today, this morning, we have Earth's surface pressure, which is 1 atmosphere. And if we think about that in the framework of gigapascals, which is the unit that I will be using to describe most pressures throughout this session, we are currently sitting at 0.001 gigapascals, so very low, a very small amount of pressure. If we step this up, maybe we think about pressure, for example, in our car tires, which if you've been inflating your car tires recently, it's something like 35 psi. Again, looking at that in the framework of gigapascals, we're still very low, it's still very small. 0.0002. So very, very low pressures in this context. And then maybe if we take ourselves to sort of the extremes of what we can experience on the surface of the planet, so at the bottom of sort of the depths of the ocean, at the bottom of the Mariana Trench, we have this crushing pressure, all strange looking fish existing in these high pressure conditions. We've sort of moved forward by a few orders of magnitude, but we're still at less than a gigapascal, right? 0.1 GPa. If we keep burrowing further down and take ourselves to the core of our own planet, so the Earth's core, now we're really getting somewhere. We've got pressures in the vicinity of 360 GPa. And so a lot of the pressures that I'm talking about today will be in this range, this hundreds of gigapascal range, where we're thinking of environments like planetary cores. Now, this isn't the full extent of what we can reach. Um, if we use sort of very intense laser drives and very cleverly designed experiments, we can actually extend our reach up into the terapascal regime, so pressures in excess of 1,000 gigapascal. And what I'm showing on the left-hand side here are a series of papers which showcase beautiful data sets collected at the National Ignition Facility here at Livermore, where all of these materials have been taken to the most extreme pressures that we can practically sort of make and study on Earth in the lab. And while this is very cool, and this is obviously a very extreme level of pressure that we can get to, it isn't the end of the story, just to kind of put everything in a slightly different context. If we think even just to the core of our own sun, we're looking at pressures that are in the millions of gigapascals, the 25 million gigapascal. So all of this is to say it is very cool and very impressive that we can access these states in the lab on the surface of the planet. But it's not the end of the story. There exists a universe around us where pressure is happening at something much larger than we could ever currently realize in the lab. Okay, so we're kind of all on the same page. We're talking about very high pressure. The other thing I would like everybody to become sort of familiar with at the beginning of this talk is the concept of a phase diagram. Again, I'm sure everybody in this talk has seen one of these before, but just in case. What I'm showing here is a dummy phase diagram. This isn't a phase diagram of a real material, but it has a lot of the same features as a real phase diagram. So we've got a melt curve, so a boundary between our liquid and solid phase. We also have a phase transition here between two solid phases. So phase one, phase two, doesn't really matter what they are, but two different structural phases. In this phase diagram, we're looking at it in pressure and temperature space, so increasing pressure on the x-axis, increasing temperature on the y-axis. And if we want to map out a phase diagram for a given material, we have a few different techniques at our disposal to do so. The first one that I'm showing here is static compression techniques. So this can be using things like diamond anvil cells. And this is a very sort of well-established and strong and stable technique for generating these extreme pressure states. And the way it works is to sort of simplify it, you have two diamonds. You have a sort of chamber in the middle where your sample goes, a metal gasket around the outside, usually some sort of pressure transmitting medium in the chamber, and you can squash these diamonds closer together and really increase the pressure in your sample. Now, not all diamond anvil cells are created equal. We have sort of traditional diamond anvil cell or DAC geometries, which reliably can get us to pressures in the hundreds of GPa in the lab, sort of setup dependent, material dependent, but we can sort of very reliably access this regime, which is absolutely fantastic. But we also have extended DAC geometries, so things like toroidal DACs or double stage DACs. And there have been reported pressures of sort of up to a terapascal that have been accessed during using these geometries. And we're certainly not confined to making measurements at room temperature conditions. Sort of in the context of this phase diagram, if we wanted to look at higher temperatures, we could employ techniques such as resistive heating or laser heating, which again, material dependent, but could get us up to temperatures of something like 5,000 Kelvin. And you might be thinking, oh, well, great, we've got all these techniques. Surely we can map out the majority of what you're showing here in this phase diagram. Sadly, that's not true. A lot of these techniques are incredibly difficult to sort of realize in the lab. And so I think it would be an incredibly hard experiment to have a double stage DAC at a terapascal, which is also laser heated to thousands of Kelvin. And so while these techniques are very good and give us very nice data in these extreme states, there is still a question mark left on certain areas of a phase diagram in extreme conditions that we can't access using these techniques. So, for instance, if we wanted to know about this phase one, phase two boundary up at high temperatures, we'd have a hard time knowing about that using these techniques. So, another tool that we have in our toolkit in the high pressure community is obviously laser-driven experiments. So, in a laser-driven experiment, we're sort of looking at a setup as I'm showing on the left-hand side here. We have a laser which is incident on a target package, which is typically made up of multiple layers, including an ablator, a sample, and then some sort of window at the back. The ablator is typically a low Z material, and this is the section of the target that interacts directly with the laser. What happens is our laser is incident, and it creates this big plume of plasma on the outside of the target. In a sort of reaction to this plasma plume, a compression wave is launched into our target package, and this is done via something called the rocket blow-off model. And as this compression wave enters our target, it transits through the ablator, sort of progresses forward, compressing everything as it goes, enters the sample, traverses the sample, and so we sort of compress this whole package that way. Now, just to give an idea of the scale of this type of experiment, typically the layers in this physics package are on the order of microns, tens of microns, and our laser driver is on the order of nanoseconds or tens of nanoseconds. So these experiments are very small and they're very, very quick. And historically, there have been sort of two main modes of doing this type of compression experiment, right? The first is shock compression. And when you shock a sample, you sort of end up in a pressure state that is on a curve called the Hugonio. And that's this red curve that I'm showing here on the phase diagram. Now, the Hugonio is essentially is defined as a locus of states that are accessible via shock compression. And one thing that you'll notice about it on this phase diagram is it increases in temperature quite rapidly as it increases in pressure. So this is a very sharp shock compression. The other option that we have quite well developed on hand is ramp compression. And this is a lower entropy process. And as a consequence, the compression path through pressure temperature space occurs at much lower temperatures. And it's represented typically by an isentrope or really a quasi-isentrope. Now, I just want to go into slightly more detail about these two methods of compression before we move on. If you wanted to launch a shock compression in your sample, the pulse shape would look very different from your laser than if you wanted to launch a ramp, right? For a shock compression, you have something where the laser power is on and it's held for a while and it's turned off. And this sudden, intense wall of laser intensity launches a very sharp and rapid compression shock through your sample. In contrast to this, if we're doing ramp compression, you'll notice there's a marked difference in the pulse shape. We have something that's more gradually increasing in power as time goes on. And when we're doing these types of compression, obviously we are conserving sort of mass, energy, momentum. But the way that this looks in these two different types of equations is slightly different. In these two types of compression is slightly different. In a shock compression, we have this very fast, sharp shock wave, represented by US here, which jumps our state from uncompressed to compressed. So this is a very discontinuous transition, right? And so we're moving from one pressure and density and energy very sharply to a compressed state. By contrast, in our ramp compression, it's not a discontinuous process. You could think of it as a series of very, very, very small shock steps that are adding together to give this more continuous compression. And so rather than a shock wave tearing through our sample at a very fast shock velocity, we have a compression wave moving at something more like a sound velocity. So this is a lower entropy process. And you can see that this is reflected in the way that we treat our conservation equations. For this process, we've got a couple of integrals in the mix there. But what this essentially means is this lower entropy, even though temperature is not directly addressed in these equations, this inherently gives us a lower temperature in our sample. And you might be thinking, great, well, that's very nice. We can do the shock compression, we can do the ramp compression, we can see these two curves that we could sort of explore. But what about this area in between, right? Earlier we discussed that maybe we might want to find out what's going on between this phase one, phase two boundary, and neither of these compression paths is going to really get us there. And so this is where shock ramp compression comes in. So if we are to launch something like a complex compression path into our sample, inherently this requires complex pulse shaping. And so what I'm showing on the left-hand side here is an example of a shock ramp pulse shape. I've sort of broken it down into two sections. So the first section you'll notice is a sudden step up in laser power, and this is very reminiscent of those shock profiles that I was showing earlier. And if we tune the sort of height of this step here, we can tune what shock level we reach, right? If we have a low step, we can get ourselves to a lower point on the Eugonio. If we put a bit more energy in this first shock step, then we can get ourselves to a higher point. And then the pulse shape following this initial shock then has a sort of gradual curving slope and intensity more reminiscent of ramp compression. And what this does is it takes us from our initial shock step that we've reached with the first part of the pulse and compresses us to higher pressure in a lower entropy way. So we're not increasing the temperature as much as we would a shock. And so I have these sort of green arrows coming off our shock states, which are loosely representative of isotopes traveling off the shock state. And so you can see if you wanted to map out this phase boundary, what you could do is you could tailor your pulse shape so that you are gradually stepping up in shock pressure for one of your shots. So you would shock, ramp, and then you could probe with whatever diagnostic you're using at this state. And then you could do another experiment where you shock to a slightly higher level, ramp, and then probe here. And so by incrementally changing our laser drive pulse shape, we're able to access all of these states in between the Hugonio and the isentrope. Now, this makes it sound quite easy. These are, in fact, incredibly difficult experiments to carry out. And I'm going to go into some detail about that. The first hurdle is that in order to obtain one of these pulse shapes, you need to be at a facility with incredibly advanced laser pulse shaping techniques. And two such facilities that we're very fortunate to have here in the US are the NIF, the National Ignition Facility, which is located here at Lawrence Livermore Labs. And we also have the Laboratory for Laser Energetics at the University of Rochester. This is where specifically the Omega EP laser is located. Both of these facilities are where all of the data that I'm about to show, sort of in the coming slides, that have been shock ramp compressed, all of the data was collected at these two facilities. And there's a lot of similarities between these two facilities. Typically, we have a chamber. As you can see here, we've got the NIF chamber and the Omega chamber. And this is where the experiment occurs. So we have our target package in the chamber. We have our diagnostics in the chamber. We create our X-rays in the chamber at these facilities by irradiating a foil. And while this experiment is happening, the chamber is being evacuated. So we're doing this whole thing under vacuum in a sort of enclosed environment. And we have various different laser beams pointing into the chamber, and that is what sort of one generates our X-rays from this foil, but two also delivers this pulse shape that we've been discussing, sort of the key to this compression technique. And so, it's all well and good. We can have a nice pulse shape, we can have a nice compression path, but ultimately what we want to do is learn something about the state of our sample when it is in this compressed state. And one of the options that we have for doing that is employing X-ray diffraction. And this is something that's available at both of those facilities. And so I just kind of want to talk through some of the details of that now. At the Omega EP facility, we are collecting our diffraction data using Pixadip. So this is powder X-ray diffraction image plates. The way that it works is we have our target, so our multi-layered ablator sample window target sitting on the front of the Pixadip box. A laser drive comes in, and this is what launches the compression within our target. During the entirety of the experiment, we have another laser coming in and looking at the rear surface of our target. I'll talk in a bit more detail about this in a moment, but this is our VISAR diagnostic. This is something that we measure velocity with, and it's one of the ways that we infer pressure within our experiments. And then the other thing we have here is our X-ray source. So this is the foil. We have some number of lasers pointed at this foil, and we drive it at the right time so that we can send our X-rays through our compressed sample and take a snapshot of what is going on in our sample at that moment. And so the X-ray diffraction is the X-rays are coming in, they're diffracted by the sample, and the diffraction is collected by the image plates on the walls of this Pixadip. And I've got a small video here which is illustrating that. So we've got our laser drive. You can see our targets being ablated there at the surface. There's all that blow off. Our X-rays are coming through, and we're collecting all of the diffraction data on the walls of this Pixadip box here. When we're doing experiments on NIF, quite a similar setup. Instead of Pixadip, we have something called TARDIS, which is our target diffraction in situ. And instead of a box, we have something that looks slightly more like a watermelon here. So we have image plates on the rind and on the top and the bottom. But still similar to the other setup, we have our target sitting on the front. We have our visor laser coming in the back to make a velocity measurement. But we also have two X-ray sources. So one bonus of doing these experiments at NIF is that rather than just taking one X-ray snapshot during our compression path, we can actually take two snapshots, which is great, double the data. That's a real bonus for us in terms of interpreting what's going on. And on the right-hand side here, I'm just showing an example of some of this diffraction data that's collected sort of on the rind and on the image plates. It's been de-warped into a view where we've got our nice Dubai Scherer rings looking sort of circular there for us. Very nice. So we've got our compression with our complex pole shape. We've got our diffraction coming in to let us know what's going on in the sample. The other thing that I'd mentioned here in this setup is our visor. Now, this is an incredibly important tool, especially for these shock ramp type of experiments, because this is really what allows us an insight into what's going on in terms of the pressure within our sample. So during the experiment, the visor laser comes through. It is transiting our transparent window on the rear surface of our physics package, and it is reflected from our shiny sample surface. If your sample is not something that's shiny, that's okay. You can add a small shiny flash coating layer to that, but it does have to be reflecting this laser light. And the data that is collected, it's sort of streaked data, and you can see that as the shockwave reaches this interface between the sample and the window, we've got a motion in these fringes, right? And this is sort of a measure of the Doppler shift of our moving target. And so by analyzing the motion of these fringes, what we can do is we can interpret a velocity in our target. Now, from that velocity, it's a bit of a step to get to pressure. And the way that we do this is by a method called characteristics analysis. So the pressure at like the probe time during our experiment is determined using this sort of one-dimensional characteristics analysis. And our visor data here serves as a boundary condition. So the inputs for the characteristics analysis are things like the visor, the measured target metrology, so the thickness of the layers of our target package, and also tabulated equations of state, so equations of state for the materials in the target package. And then through Lagrangian sound speed and particle velocity relations for each of the layers, we can integrate the characteristics equations backwards and work out the pressure in the sample during the probe time. And so what this is doing is it's reconstructing sort of the stress particle velocity states throughout the target as a function of both time and position. And it's accounting for any sort of interactions, any interfaces between the layers and the targets. And so from this, we're getting the pressure. And so you can see here, I'm showing an example of this characteristics. This is taken from our gold PRL paper. There's quite a bit of information about this in the supplementary material if you're interested to learn more. But essentially, we run our characteristics analysis, and this gives us a view of the pressure distribution within the gold state during the experiment. It gives us an idea of the median pressure in the sample state during the experiment. And we also have a distribution of the pressure states. Now, the specific code that we used in our experiment is one that's been developed at the lab by Ian Ocampo, who's postdoc here. And what he has incorporated is a sort of Monte Carlo method of folding in uncertainties. So uncertainties in our measured velocity, uncertainties in our measured thicknesses, and uncertainties in the equation of state to sort of give us a view of what the pressure might be in light of the uncertainties of the experiment. Okay, so just to kind of bring a summary here before we get into the details of things, what we've done is we've laid out an experimental setup. Okay, we've got this really nice pulse shaping. We're putting these pulses into our physics package. And at the right time, we are sending our X-rays through to take a snapshot of structurally what's going on in the sample. For the whole experiment, we're doing Visor measurements so that we can sort of afterwards make a measurement of the pressure that we experience within the sample. So fantastic, we've got this set up. Now let's talk about some applications. So obviously the first thing that I would like to talk about is our recent gold PRL paper. Um, the title of the paper is shown here. You'll notice it's BCC phase transition in gold at terapascal pressures. And this is a very nice result that we discuss in this paper. This is the highest pressure measurement of gold that's been made. This is the highest sort of structural constraint of gold, the highest pressure structural constraint of gold that exists. And that's very nice, and obviously we're all very proud of that work. And it's the hook of the paper for a reason. However, what I want to talk about is another aspect of the work. So the other aspect of the work in this paper is a series of shock ramp experiments from Omega EP, which gave us some, frankly, very beautiful diffraction data, but importantly, helped us reconcile this sort of long-standing discrepancy between different models of what's going on in the gold phase diagram. So just to kind of put this in some context, before our paper was published, there were a couple of ideas from various different theoretical calculations of what might be happening in the gold phase diagram, right? There's this one model that was published in 2019, which describes a structural transition from the face-centered cubic, which is the ambient structure of gold, describes a transition from the FCC structure to a body-centered BCC structure at some pressure below 400 GPa, right? Contrastingly, there's also a description of the gold phase diagram as maintaining its FCC structure up to about 600 GPa and then transitioning to an HCP structure. Something that both of these models have had to take into account is the fact that we know that on the Hugonio, the gold does transition to a BCC structure before melting, right? We have experimental data that shows that sort of unambiguously. In this model, it's kind of addressing that by saying, okay, well, perhaps in the high temperature portion, we're creeping into the BCC phase here with the Hugonio before we melt. In this version, we're talking about more of a high temperature pocket of a BCC phase. So sort of two different ways of addressing that. The other thing that is present on these plots, we have a series of crosses down here. These represent room temperature diamond anvil cell experiments, which are showing that actually the FCC structure of gold is present up until quite high pressures, at least 600 GPa, and depending on sort of what you believe from results, maybe even a terapascal. So there is quite some evidence of FCC persisting to higher pressures. And you might think, okay, we're looking at these two contrasting models of a phase diagram. It's not uncommon to have different theoretical predictions of a phase diagram, and you'd be quite right. What is slightly more uncommon is having contrasting experimental results of what is happening in a phase diagram. So on the right-hand side here, it's the same prediction of a phase diagram, but what I want to highlight is this ramp compression blue arrow. And what this represents is a series of ramp compression experiments conducted by Federica Capari, where they saw up to about 600 GPa, there was no transition to BCC phase in gold. So just FCC all the way up to 600 under ramp compression. On the left-hand side here, I'm showing a paper that was published in PRB in 2021. And what the results from this paper show are actually something that's more supportive of the alternative phase diagram, whereby just below 400 GPa, there is in fact a transition from this purple FCC phase to this blue BCC phase. And so we've really got two things that are sort of published and contradicting each other. Now, at the time, there was some work being done by the XAFS group at Livermore Lab, and this was headed by Hong Seo. And this was work done on ramp compressed copper, and I've got a reference to this later on in the slides. But this was a really nice piece of work. And one of the findings was that if in your target package you have a diamond sandwich, and by that I mean a diamond layer on either side of your sample, there can be quite a bit of excess heating, right? And when we look at this paper, the target package that was used, some of them did indeed have these diamond sandwiches. And so one thought that we had was, well, perhaps these results were driven by ramp compression pulse, but actually they're representing something that is at significantly higher temperature, right? Maybe this BCC phase exists, but because of the diamond sandwich in the target package, it exists at much higher temperature. And so what we've got here is really the perfect use case for this shock ramp compression path that I've been describing, right? What we could do feasibly is design a series of shock ramps where we start off with a relatively low shock and probe at a lower temperature, and then incrementally increase this shock state, probe at increasingly higher temperatures, and step up and see where does this BCC phase come in, right? This would give us an opportunity to constrain this. And so that is precisely what we did. We designed a series of experiments at the Omega EP facility in Rochester. Again, using this Pixadip setup that I've mentioned previously. I'm just sort of giving a view of the target package here, of the diffraction here, and the target package on the right-hand side. Now, one thing that you'll notice is that this target package is slightly more involved than the ablator sample window version that I was showing earlier. So I just want to talk through that a little bit. What we have here in this target is we've got our beryllium ablator layer. So this is where our compression wave is launched. We've got a lead heat shield, and the purpose of this heat shield is to sort of protect our gold sample layer from additional heating from the ablation plasma, sort of generated at the front of the target. We have a secondary beryllium layer. This sort of acts as a nice spacer between our sample and our very hot heat shield here. Then we have our sample that we're interested in and our lift window at the back. This is where our visor comes through. The other thing to point out, which will become relevant later, is that on the back of our targets, we also have this platinum pinhole. This is a layer that is not compressed. This is ambient platinum, and it appears in the diffraction as such. And what this allows us to do is to calibrate our diffraction patterns so that we can correctly pull out a density of our sample layer. And then on the right-hand side, what I'm going to show here is a hydrocode simulation of this experiment. Now, these experiments, as you can imagine, quite difficult to field, and really we do rely on hydrocode simulations to do the design work, not only so that we can reach the correct pressure and temperature states, but also so that we know when to probe with our diagnostics. And the hydrocode simulation that I'm showing on the left-hand side from this gold project, this is design work done by Tom Lockard, who at this point is an absolute expert in designing these shock ramp experiments. He's been on quite a few campaigns. And so this is kind of what we're looking at when we're planning the experiment. So on this plot, on the y-axis, we have depth into the target. So we've got our beryllium layer, our lead heat shield, our second beryllium layer, the gold sample, and our lift window. And on the y-axis, I've quite unhelpfully cropped out the label here, but this is showing the time, right? And so the colors on this graph represent pressure at different times throughout our compression event. So we have 0 GPa as a dark blue and sort of very high pressures as a dark red. And so what's going on here is we've got our compression wave initiated and it's traveling through our beryllium layer, and then it reaches this lead interface. And so you can see the compression wave continues through, it transits the lead, it transits the beryllium. But every time it reaches an interface, there is a reverberation wave that comes back, right? And so you can imagine in a physics package with this many interfaces, there are quite a few reverberations to be taken into consideration. And in fact, as time progresses on, you'll see that things become a bit messy. There's a lot of interacting waves. And especially in our gold sample, we have our initial shock, but then we also have this ringing up of pressure as our compression waves are sort of ringing back and forward within the layer. And so this ringing continues until we eventually reach what is a relatively uniform pressure state within the sample. And so these hydrodynamic simulations allow us to know when that is. so that we know when to time our X-rays. And so once we're at peak compression, we can send our X-rays through and then make a measurement of the structure of our material. And I just want to stress the point, the timescales that we're working on here are nanosecond timescales. The length scales are sort of tens of microns to hundreds of microns. Um, and you might think this is a very difficult feat to pull off using a simulation like this to time something so intricately in these experiments. But we do manage to do it, and that sort of speaks to the quality of the design work that is being done and also the quality of the equation of states that are used in these designs to sort of model these materials. So it really is, it takes a lot, but it does work. And so to cut a long story short, we'll come to sort of the results of this gold paper, which I'm showing here. On the left-hand side, I've got a phase diagram. It's a very messy phase diagram because I've included all of the predicted phase boundaries, right? There's the red boundaries which show this predicted BCC transition at 400 GPa. These blue phase boundaries that predict that FCC is stable until much higher pressures. And then additionally, I've also included some green phase boundaries which were calculated by one of our colleagues, Stefano Raccioppi, as part of this work, which sort of agree kind of with the results that we're seeing here and that there is a high pressure BCC phase predicted. I don't really have time to get into it in this talk today, but it is incredibly interesting and a nice work. And there is, again, a thorough accounting of this in our supplementary materials, which is sort of quite detailed. Okay, so in terms of the actual data on this phase diagram, we have, the data from the hook line and the title, right? We've got this BCC. In fact, what we saw was a mix of BCC and FCC up at these really high pressures in the terapascal regime. On the right-hand side, I'm showing our diffraction data. So we can see these red tick marks are indicative of FCC peaks. These blue crosses are our BCC peaks here. And sort of to sort of bring our story to a close, looking at these shock ramp compression data, you'll notice that all of the squares are red. And that is because all we saw in this regime was FCC gold. There was no indication of BCC gold. And we went to quite some pains to look at this. There were a few iterations of target designs. One of the considerations in these types of experiments is obviously if you have a multi-layered target, you need to be careful of overlapping diffraction peaks, right? We have some peaks in our profiles here that are from our platinum calibrant, which is uncompressed. And then the other peaks that we have here are from our FCC gold. If you were going to use something like an aluminum layer in your package, which we did early on, that's going to cause you problems because you'll have something that is overlapping with your gold peaks. So after much iteration of target design, we found something that gave us this really unambiguous FCC data. And so you might be thinking, oh, well, what about that? What about that BCC transition data that we were talking about earlier on? Could it perhaps be the case that that was just incredibly hot and sort of even hotter than any of the stuff that we've described here from these sort of quasi-isentropes coming off a shock state? And actually, this work when we sort of collected this data, this prompted us to go back and look at the data again from the original paper. I will say there's an awful lot of overlap between the authors of that original paper and this recent PRL. So we sort of took it upon ourselves to go back, look at the data, and with sort of improvements in the analysis techniques and improvements in background subtraction, we actually found that the original data set was consistent with FCC. So there wasn't actually a measured transition to BCC. It was just a very difficult data set to analyze in terms of overlapping peaks. And advances in our diffraction analysis techniques have allowed us to see that actually it was FCC. So what that means additionally for this gold paper is the observation of this BCC up in the terapascal regime is actually the first off-Hugonio BCC measurement made using these types of techniques, which is very, very exciting. So this is nice. This is great. We've sort of shown that this shock ramp compression can be used to resolve questions about existing phase diagrams. And this isn't the only piece of published work using these techniques. There's also a paper from a couple of years ago from Rick Krause. This contains data collected on the NIF where shock ramp compression was used to investigate the iron melt curve, quite high pressures, so extending all the way up to the terapascal regime. And in this experiment, the primary diagnostic was again diffraction, so using the TARDIS platform. And by looking at the diffraction data and seeing either sort of solid ion peaks or diffuse liquid signal, you could sort of put some constraint on where this melt curve might lie, which is great. That's nice. So now we've got this technique. It's good for looking at phase diagrams, phase boundaries. It's good for looking at melt curves. Um, but an obvious elephant in the room, I think, is what is the temperature, right? It's all well and good saying that we can get to these different pressure temperature states, but really we need to have good constraint of the temperature. And you'll notice none of those sort of measurement techniques that I'd mentioned there were doing any temperature constraint. And so when we're talking about these compression techniques, we've been talking about shock to a point on the Hugonio, and we've been talking about some sort of isentrope coming off as we're doing our ramp compression. But we know that that's not true. We know that that's not real. We know that in a true experiment, there's a lot of additional heating that's happening. We've got heating uh, from work within the sample. We've got heating from our ablation plasma at the front of the physics package. And if we're generating our X-rays with a foil in the chamber, we've got additional heating from those X-rays being generated. So when we've been giving these isotopes coming from a measured shock state, typically we've been given these as a lower bound on the temperature. In reality, we would expect the temperatures to be a little bit higher. Now, if you did, for example, want to measure temperature in this type of experiment, there are a couple of options accessible to you. And one that I'm going to describe now, I am using in sort of this ongoing unpublished work, which is sort of developing our understanding of the ion melt curve. So one of these techniques is XAFs. And I'm fairly sure you're not allowed to give an XAFs talk without at least flashing up the XAFs equation, which is not the nicest to look at. Luckily, we don't have to understand everything that's going on in here. The main points I would like you to take away from this are that sort of when we have this scattering, so when you have our X-rays sort of coming in, exciting a core electron, and then we've got this outgoing photoelectron, which is scattering from neighbor atoms and interfering with itself and interfering with the absorber and sort of producing these oscillations that we know as our XF signal, right? This process is sensitive to obviously atomic density, right? To density, we've got these atomic distance terms in the equation here. And we can see this in this sort of simulated XAFS data that we have down at the bottom. When we're moving to higher densities, you can see that there is a shift in the XAFS oscillations. But also it's sensitive to temperature. And it's sensitive to temperature by means of the mean square relative displacement. And that's this sort of sigma squared term up here. And practically what this looks like in XAFS data is a reduction in the amplitude of these oscillations as you're moving to higher temperature. So again, on the bottom left-hand side here, I've got some simulated XAFS data. And when we're at relatively low temperatures, so 1000 Kelvin, we've got really high amplitude oscillations. By the time we get to 7000 Kelvin, we really drop those oscillations. And so what we can do is we can make some XAFS measurements and we can use that data to infer temperature. And so some experiments that we're currently doing at Omega EP are doing just this, right? We're doing sort of a 1-2 punch approach. We're employing these shock ramp compression techniques to get ourselves to states that are close to the ion melt curve. So on the left-hand side here, I've got an ion melt curve. I have sort of the tail end of the Hugonio coming up here. We've got this purple curve, which is the predicted melt curve from Rick Krause's work. We've got this red curve, which is the predicted melt curve from theoretical work by Christine Wu here at Livermore. And these 2 points represent 2 points that have been accessed using this shock ramp technique, right? And so the first section of this 1-2 punch is we shock ramp compress and we take an X-ray diffraction snapshot, as I've previously described. And the data that we're collecting, really beautiful, right? In the compression regime where we're just below the melt curve, we're seeing very strong signal from HCP ion, and it's really unambiguously HCP ion, right? There's no overlapping peaks from anything else. Our calibrant peaks, which I've highlighted in green on these diffraction patterns, are quite far away from our experimental peaks. And we're seeing sort of really nicely the first full 3 peaks of the HCP structure. So it's really quite unambiguous what is going on there. As we push up to higher temperatures, we sort of lose sight of those peaks, right? Those solid diffraction peaks go away. And now typically when you think of liquid diffraction, you think of this nice diffuse scattering signal. We don't see that here. The reason for that is we are using, first of all, very thin iron layers in these experiments, something on the order of 6 microns. And this is unfortunately below the threshold in this sort of image plate diffraction setup where we would be able to see liquid signal. So typically in these types of experiments, we are taking the loss of any solid diffraction peaks as sort of us entering the liquid regime. So we've got this diffraction data, which is constraining our structure. What we can then do is take the same physics package, we can use the same laser pulse drive, we can probe at the same time. So we're basically repeating this experiment, but instead of running diffraction as the primary diagnostic, we can run XFs, right? And so what I'm showing here on the phase diagram are sort of well, 4 data points really, but 2 repetitions. The circle represents where our diffraction data is based on a pressure from characteristics analysis being pinned to an isentrope from a shock state. And the triangle is our XFs data, so our repetition of the shot dealt with in the same way. And you can see we've done a pretty good job of reproducing this. One thing I will say about the sort of pulse shaping of these facilities, it's very good and it's incredibly reproducible. So really, it's cutting edge technology that is allowing us to do these types of experiments. Now, unfortunately, this isn't the part of the talk where I give you a temperature constraint of the iron melt curve. This is work that is ongoing. In order to infer the temperature from our XFs data, we have to do a series of QMD runs where we're simulating iron XFs at a series of temperatures and densities, and then comparing them to our data that we've collected here. One thing that we can see that's quite nice is there is a marked difference between the sort of character of solid and liquid XFs. We can see that in the Zanes where there's a difference across the sort of edge here. And we can also see it in the differential of the edge itself. So we are able to differentiate in these experiments between solid and liquid XFs. And now the work begins to try and extract a temperature. And so this is very nice. This is very exciting. What we're hoping to do here is extend this up to much higher pressures. So presently we have data up to about just under 700 GPa. And what we want to do is really look in this regime where these two melt curves diverge so that we can have some comment on the difference between these two predicted melt curves based on in situ bulk temperature measurements. So very nice, very nice. Now, obviously, XFs is not the only means of extracting a temperature measurement from a dynamically compressed system, but it is one of the more developed ones at the moment. What I'm showing here are sort of 5 different methods that are emerging and are being developed for use in dynamically compressed experiments for getting a bulk temperature. Now, the 2 that I'm showing on the left-hand side highlighted in blue, these are techniques that we've been putting quite some work into developing at Livermore on data sets that we've collected on NIF and Omega EP. On the right-hand side, I'm showing other emerging techniques. These techniques require higher signal to noise. And so if we want to employ these in our experiments, we can't really do them at these facilities where we're generating our X-rays with foils and using image plates. What we need to do is we need to look to facilities where we have much more brilliant, much brighter X-rays. So facilities like synchrotrons and facilities like X-ray free electron lasers like LCLS down in Stanford or European XFAL in Hamburg. So I'm going to briefly go through and describe these techniques in a little bit of detail. One thing I would like you to bear in mind is all of this work is quite recent. If I'm showing any papers sort of published work, you'll notice the dates on the paper are quite recent. These are all techniques that are very much being developed. And so one of something that's going to be a very important piece of work in the coming years for the field is cross-validation of these techniques, right? What we want to do is repeat sort of the same compression experiment and employ each of these different techniques and just check that they're all giving us the same value for the temperature. Okay, so just to kind of go through these very quickly, if you have diffraction data, temperature sort of increases atomic mean square displacement, right? And so we have these Bragg peaks. And And these peaks are reduced by something called the Debye-Waller factor, which affects high angle peaks more than it affects low angle peaks, right? And so if we look at the relative intensity of these peaks in a hot sample versus a cold sample, we can extract a temperature sort of using a Debye model, right? And so this is sort of preliminary work, which is sort of really being led by Amy Janae here at the lab. She has a really nice data set on lead, where she is currently using this technique to extract a temperature. Comments on this technique is it's only really valid if you're in the solid regime. You do need these sort of intense peaks in order to infer a temperature. You can't really do this on a diffuse liquid scattering signal. And also it relies on a Debye model, right? But it is a good technique that is being developed. Another technique, obviously, is XAFs, as we've discussed. Here, finally, is the reference to Hong's paper. So this is this nice work that I was talking about earlier on measuring temperature in copper. This is the one where we saw the increased heating from the diamond sandwich. It's a fantastic, fantastic paper, really, really nice work. Again, just showing the dropping of the amplitude of these oscillations as we're going up to high temperatures. Again, this technique does rely on sort of QMD simulations in the way that we are interpreting the temperature here. So it does sort of rely on a model. And I've written for temperature range below melt question mark. I think analyzing liquid XAFs is something in this regime that's relatively new, and it's something that we're working on at the moment. So it remains to be seen what we can do with that data. Okay, and so now we're talking about these techniques that are being developed at XFEL. So the first one I've got here is thermal diffuse scattering. So we're back to X-ray diffraction again. This time, instead of looking at the relative intensity of the diffraction peaks, actually what we're looking at is this diffuse scattering between the peaks. So temperature increases inelastic phonon scattering between these Bragg peaks, right? And so the intensity of this diffuse scattering scales with the phonon population. And so by fitting it, and again by using a Debye-Waller framework, we can infer a temperature. And this work is really being led at the moment by a group at the University of Oxford, so Justin Walk and Paddy Hayway. They're doing sort of tremendous work in getting this to a state where you can apply it to various different materials with data sets collected. So sort of not just at European XFEL, but maybe also at other facilities. Again, this technique relies on a model, and again, this technique is only good below melt since you can't really have this diffuse signal from a liquid. And then finally, these last two techniques, these are MEV inelastic X-ray scattering techniques. For forward MEV IXS, we're measuring T through measuring temperature through detailed balance. We're looking at the asymmetry in the phonon spectrum. So MEV resolution measurements at small momentum transfer, so Q is the momentum. They allow us to resolve the Stokes and anti-Stokes phonon peaks, right? And at finite temperature, phonon creation and annihilation aren't equally probable. And so by fitting the ratio of these peaks, what we can do is we can pull out a temperature. And the nice thing about this is it is not model dependent. So we don't need an ERS or a Debye assumption. One of the downsides of this is it's only viable in a sort of temperature range where your temperature is comparable to the phonon energy. So we're talking about a third of phonon energy up to 3 times phonon energy. So you're slightly limited in the range that you can explore, but it's nice that it doesn't rely on a model the same way that the first 3 techniques do. And then the final technique that I'm showing here very quickly is backwards MEV IXS. And so this is measuring temperature from thermal broadening of the elastic or Rayleigh peak at high momentum transfer, right? And so thermal motion is what's causing like the Doppler broadening of these scattered photons. By fitting this this peak, what you can do is infer the temperature. And so the data that I'm showing here is from superheated gold at 19,000 Kelvin. You can see the hot one is much broader. This can also be applied to dynamically compressed techniques. So this is a sample at ambient pressure, but very hot. We have data that we've collected in a collaboration with Tom White and Bob Nagler at LCLS, where we have applied this technique to shock compressed iron to great success. So that we don't really have published work on that yet, but it's coming through, and we've had some very nice results. So okay, we're at the end. We're on the final slide. I think the point I want to get across is ultimately we're not just striving to push to higher pressures, right? Now we're sort of seeking thermodynamic closure. We want to define a trajectory in pressure, temperature, space, and we don't really want to be relying on models as much as we currently are. And in order to do this, we do need those temperature diagnostics that I've just been describing. And so for me, I guess the key takeaways are this. Developments in laser pulse shaping have given us this tremendous gift, right? We're now able to field these experiments that explore the space between a Hugonio and an isentrope. But if we want to establish this technique as sort of a robust technique for mapping out phase boundaries and melt curves at extreme conditions, we need these reliable bulk temperature measurements. And so presently we're at a very exciting time in the field where the combination of these pulse shaping techniques and these structural diagnostics and these emerging temperature measurement techniques together are ushering in a new era of experiments, right? And so we've got greater power to more thoroughly explore matter at extreme conditions. So that's kind of all I've got. I obviously would like to thank everybody who is working on these experiments with me. Especially, I would like to give a large thanks to the teams at the National Ignition Facility and the Laboratory for Laser Energetics, without whom none of this work would be possible. So thank you very much. And in the time we've got left, I'm happy to take any questions.
Thank you very much, Amy, for a beautiful talk. Very pedagogic and very interesting, especially the work on gold and then all these new developments for temperature measurement. Talk is open for questions, comments. Just unmute yourself, put your questions or comments in the chat.
Can I go
Raise your
first,
hand.
Ross?
Go ahead, Urshan. Yes.
Well, when I see X-ray Ask X-ray scattering, I get excited, obviously. I have two questions, both XFs and IXS measurements. What's the time scale to collect this data?
So in order for these techniques to be applicable to the dynamic compression experiments that I'm talking about, inherently the timescale has to be nanosecond timescale.
So can you collect XFs data in 1 nanosecond?
Yes, absolutely, absolutely. And we've shown this repeatedly on facilities like NIF. We have published work where our X-ray probe time is between 1 and 2 nanoseconds. Obviously, there is a signal consideration. And so if you're using something with slightly worse scattering, you obviously want to bump up your X-ray collection time. But yes, we very much can do this on the nanosecond timescale.
Thank you.
Thank you. Yes, Daniel.
Thank you, Amy. Very nice talk. I really enjoyed it. A question about the XFs, the by-Waller factors. You showed the very nice simulations of the temperature dependence of the XF signal, but obviously the by-Waller factors also depend on pressure, and they go on opposite ways as the phonons harden under pressure. And I believe you can constrain those with a Grunasian parameter. The first question is, are you using that Grunasian parameter to constrain the frequency of these vibrations and the temperature? That's the first one. And the second question is, how about, are you assuming that as you ramp compress, shock compress these systems, that there is no static disorder that is added in the local structure, that even before it becomes liquid, if there is any static disorder that is changing as you ramp it, it will bias and shift the by-Waller factors in weird way because there is a static component is on top of this dynamic component.
Both very good questions. So in terms of the analysis that we do on the XFs data, obviously there is a way to analyze. You can look at XFs data analytically, right? You can fit it and have different cumulant analysis for interpreting a temperature. What we are doing is we're using QMD to simulate the data to compare our collected data to, right? Now, obviously, these QMD simulations rely on a potential, which sort of make inherent assumptions about things like the Debye temperature and the Grunasian parameter. And so you're quite right in that perhaps there is some room for us not being sort of perfectly replicating real life within those potentials. And this is one of the reasons why I think it's incredibly important for us to look to these other temperature measurement techniques so that we can sort of benchmark these methods that we have that are relying on things like the Greisen parameter and the Debye temperature. We can benchmark them against techniques that do not rely on that. And so I think investigating that is going to go a long way to answering that kind of question in the coming years. For the second part, I think it can be answered the exact same way. Of course, there could be any number of things happening within these systems that we do not yet know about, right? And will they be captured in things like QMD that we're using to interpret our results? The answer might be no. And so I think as we're beginning to get a handle on these new techniques and employ these techniques, I think it's very important to do it in a way where we are checking ourselves on our methods that we are currently employing.
Yeah, thank you. Yeah, I think it's also important to remember that the way XFs measures the Debye-Waller factors is, or the Debye-Waller factor measured by XFs is really a different Debye-Waller factor than measured by diffraction and the other techniques, because it measures the relative displacement and it's biased in the way it probes the phonon density of states. But
yeah,
I'm sure you know that.
Yeah.
Yeah.
No, thanks very
Thank
much.
you.
You emphasize the importance of cross-checking techniques, and
Mm.
I'm wondering if you could summarize where the cross-checking has been most helpful or successful, because you also emphasize that certain techniques are good for different phases and different temperature regimes. And then another way of thinking about cross-checking is other methods used, for example, also on other platforms. And I'm thinking about optical methods, pyrometry, and even optical Raman for temperature constraints. So
That is a
comment on
fantastic.
those.
That's a fantastic point. So to talk about cross-checking, the cross-checking has not been done yet, right? These techniques are so new. We're really just beginning to establish them in materials that are well suited to each of these techniques. Right? In order to do the validation, cross-validation, what we need to do is identify a material that is compatible with all of these techniques in a sort of pressure temperature regime that is compatible with all of these techniques. And a few of these exist. I'm doing some work at a project at the lab at the moment where we're looking at copper, which is applicable to all 5 of those techniques that I was discussing, and there is a band of crossover in sort of shock compressed copper where you could apply them all. And so this is something that we're definitely looking to realistically do in the coming years. In terms of pyrometry, that's obviously a very interesting and good point. We do have the ability to make pyrometry measurements in these dynamic compression experiments. Obviously, they're quite difficult to field and they're a little bit limiting in terms of what you can have of the window on the back of your target package. But also, a lot of the time, they're making a surface temperature measurement. And so one thing that I think is also going to be super interesting as we sort of bring these new bulk temperature measurements into their maturity is looking at the surface temperature measurements, looking at the bulk temperature measurements and seeing if we're really looking at the same thing or whether in these types of experiments we're experiencing some kind of a gradient across our system. And sort of another field in which this becomes even more interesting is if you think about samples that aren't necessarily at full density, so like porous samples, we know from sort of models and sort of thought experiments that perhaps there is a real large discrepancy between what we're seeing on a surface temperature measurement and a bulk temperature measurement as we have this additional heating from pore collapse. And so I think establishing these bulk techniques is incredibly important for sort of understanding a wider range of systems in this high pressure regime.
Great. Thank you very much. Maybe another comment. In these X-ray diagnostics experiments broadly, and thinking about laser-driven shock or ramp shock experiments, what's the most complex structure that's been identified or constrained? Because, of course, we're looking at obviously fairly simple structures here, FCC, BCC, HCP constraints, and looking at just a few lines. So is there an example of a more complex structure, even at lower pressures? So what is the state of the art in terms of structural complexity that we can constrain?
Absolutely. In terms of these complex sort of compression paths, so far we've sort of been keeping it to easier sort of structures. And the primary reason for that is because a lot of these materials that we're looking at are things like metals, which typically have a lot of cubic structures, or maybe a HCP thrown in there. Um, and these are materials that are sort of well understood to us. If we want to develop these techniques, we want to be using materials that have sort of very well established equation of states. And so kind of inherently through developing these techniques, we've stayed in the domain of sort of simpler crystal structures. However, broadly talking about dynamic compression, sort of in general, shock compression, ramp compression, whatever, this can be used to resolve incredibly complex structures. Under shock compression, we're able to identify on the nanosecond timescale transitions in things like antimony to incommensurate host-guest structures, where sort of it's fully formed. You can sort of see all of these peaks. So there is absolutely the potential for applying these techniques to more complex systems. Just while we've been in the process of developing them, we've sort of stayed down in the simpler regime.
Right. Okay. Any more questions or comments? Well, if not, thank you very much, Amy, for a wonderful talk. Beautifully presented, and I think it'll be very valuable to the students. Thank you for allowing us to record it.
Nice. Thank you very much. And if anybody has any follow-up questions, please feel free to email me.
Great. Okay. Thank you all for joining us.
Thanks.